everyone. I hope you know me now. So welcome to, well, the topic of our course has evolved. So it's group theory and algebra. Then I immediately realized this topic is way too big. So I changed this topic immediately, as you have known, from the course outline to Lie groups and the Lie algebras. And then I go to read the book. I find this topic is still too big. So now our topic has changed again to Lie groups and the Lie algebras in the world's smallest nutshell. Okay, so there are two approaches that I can take to teach such a course. I can have a selective of topics. I can just talk really, really fast. I choose the first option because I can't really talk really fast. This is my second language. Okay, so as some of you might know, that our outline of this course is that today, let's call it the first lecture, that we'll have an introduction. So some of you might have already seen the subjects, but some of you have not. And your first question would be, what's Lie groups and the Lie algebras? So that's what we'll cover today, that's what we're actually going to talk about. And we'll ask some very important questions, including questions you should always ask when you learn a new subject. Why should we be interested? Okay. And then, today we'll cover the basics. And then, tomorrow, we'll study the structure of a group. Okay. And then, in particular, we want to look at this group called Poincare group. As we'll sure introduce this group very soon, in 5 minutes. And then we'll move on on Wednesday, we'll study the simplest but structureful group that we know. In particular, we're going to study its Lie algebra, which is SU2. SU2 is everything. It's all about SU2 for a whole class and a whole tutorial. And we'll know why on Wednesday. And then, on the fourth lecture, we'll achieve our noble goal of classify all the Lie algebras. Hopefully. If not, we'll at least classify all the rank 2 ones. Well, of course, I'll define rank 2 in that lecture. But anyway, that will be our goal. Okay, so today we'll do introduction, as I called in the other outline. I call this some first questions we want to ask. So if someone says, let's go to study Lie groups and Lie algebra, the first question you would ask, why? Should I be interested? Okay, so we'll give a motivation for that. And then, of course, the second question you say, what is a group? And then the next question, well, after we say, this is the group, we shall give some examples. Well, there will be lightning examples of finite groups, since that's another very vast and beautiful subject. That's precisely the reason that now the course has changed. And we'll introduce some examples, but we'll get all the interested readers to read chapter 1 of Georgia, or some even more other references talk about this more extensively. And then we'll swiftly move on to define what are Lie groups. After all, this is what we're interested in this course. Okay. So then we move on to topic, what I call group trivia. So if we go to a trivia competition, what kind of questions do we expect on groups? Okay. And then, if we have time, we shall introduce the representation of group and bring all our study to matrix multiplication, which I assume you have all gone through the tutorial 0, that you are very familiar with matrix multiplication. Then we'll just deal everything with matrices. Okay. So let's start with our first question. Why? Well, for our immediate interest, some of these groups we cover will show up in your QFT2 courses, which is in November. That Dan will be the fellow for that, and he'll be very angry if you don't know what's SU2, what's SU3. Okay, the consequence is very bad. Okay, and then that's the immediate interest. And of course, we can just want to learn about the subject because it's a very, very beautiful theory, as I hope I can show you at the end of the lecture when we classify them. I hope I can try to show you in every lecture. But it's a very amazingly beautiful thing. But why exactly? So let's not go to the emotional area and say the reason why we're interested in groups is because we're interested in symmetries. Okay, we are living in, well, let's say locally, approximately Minkowski space. So this is where we live. So, it's natural that we wonder what symmetries this space have. As you have learned in special relativity, we have Lorentz symmetry. You can do Lorentz transformations on observers, then they should say the same physics. Or we can just do translations. So if you just move an observer from one location to another, they should also say the same physics. And this together is known as the Poincare transformations. Poincare, I apologize for pronunciation. Okay. And also, if you're interested in, as many of our ancestors are interested, what we're made of. Well, we're made of some particles now described by the standard model, which you will see in January. Then you will see all these particles that we're made of, all the other particles that are in our universe that we're not made of. They have this local gauge symmetry called SU3 cross SU2 cross SU1. And this is nice because we're going to devote a whole class on SU2, and in the next class, almost a whole class on SU3. And the U1, hopefully, is not that hard to study. Okay, so that's, well, symmetry seems to be around. Well, just in case, some people might not be interested in particles, but for any physics system, normally it has some symmetries. Otherwise, it's too hard to study. So we're going to say they have some symmetries, and if it's broken, we're going to break it later. So either way, we'll have to be interested in symmetries to do some physics work. Okay, so let's see how exactly symmetries are actually connected back to our group. So let's start with quantum mechanics that you learned last week from Maggie. So quantum mechanics, as we know, we describe a physics system, a physics state at a certain state, which we call it psi. It's a very important letter. Okay. And also, for a physics state psi, what we're interested, of course, is some physical information. For example, we ask, suppose a system is originally in psi 1, and then it becomes psi 2, and we're interested in this probability. As we know, quantum mechanics will not determine anymore. And thus, hopefully you have already seen, it's given by the inner product square. So, if we claim the system has some sort of a symmetry, we really think, see, there is some sort of transformation seen by another observer. The psi 1 gets to transform to some psi 1 prime. Then if we'll call it a symmetry, if we get the same probability. So we really demand that the probability of psi 1 goes to psi 2 should be equals to the probability of psi 1 prime goes to psi 2 prime. Okay, so this has been studied by Wigner in 1930s. This is the time that it doesn't work. Ah, it works. Okay. So this is studied by Wigner in 1930s. Wigner pointed out that such a transformation corresponding to an operator on the state, it's either unitary and linear, or anti-unitary and antilinear. Well, this will be our focus. Why we focus on the unitary and the linear operator? Let's make a trivial observation. But if it's very enlightening, as you will see in the next class, this is an important observation, that a transformation, take observer me, to myself, called doing nothing, is the identity operator. This guy belongs to the unitary and the linear part. And for some reason, which will become clear next class, that we're more interested in the operator that can be continuously connected to identity. Okay, so now let's say that indeed there is some transformation is described by a unitary operator. Let's check this indeed works. So let's take another state and calculate the inner product. So psi 2 prime is given by u psi 2, inner product with u psi 1. And that is, as we are familiar with, that u on the bra become u dagger, and you have u on the side 1. And u dagger u is 1. That's our definition of unitary. So this one just become the inner product itself. That's cool. If the inner product is equal, then the modular square would also equal. So indeed, if the formation is described by a unitary operator that we will preserve our physical information, which is the probability. Okay. So our condition is unitary. Okay. So now, let's consider 3 observers. So what we have been discussed is about two observers. So what if we have 3? So there will be 2 transformations. So we start from psi, and then for the first transformation, it becomes psi prime. Or let's use our new knowledge that they are described by unitary operators. So what we have is psi prime equals u1 times psi. And similarly, from the second observer to the third observer would have some u2, which is another unitary operator. But these are transformations between observers. So surely we can, changing from psi directly to psi double prime, using the composition of the operators. Sorry, there's a prime there. Which tells us that psi double prime should given be by u2 times u1 times psi. But wait a second. Well, I can certainly just go from the first observer directly to the third observer. So why don't we do that? And then that should be given by the unitary operator 3, let's call. And we say this one says u2 times u1 should equal to u3 if it's a bunch of unitary operators and if it's a transformation of symmetry of the system. And then that leads us to group. So what is a group? As we say, these operators is forming a group. So what is a group? Eli.
So why does the transformation have to be unitary? Couldn't we just pick up a different phase?
Right. It's a very good question. There is something I skipped, is that you could have those phases, but then that will lead you to this projective representation, things that which will be more complicated, that will refer you to read the book. Weinberg talked about the phases in his book. So we'll just take it to that we are going to stick with this one. So indeed, there are these phases. Okay. So what is a group? Well, group is, let's call it a G, is really a set that with a multiplication defined. By multiplication, beware that the multiplication in a group maybe has nothing to do with multiplication we are familiar with, such as 2 times 3 equals 6. This multiplication, we really mean it's a binary operator. From G times G, go back to J. So what it does is, if you give me 2 elements from the set, I can give you another element. Such a map. It's called multiplication for a good reason, because for the majority of our class, it's going to be matrix multiplication. And we'll do a lot of them. Okay. So if I define the multiplication on set, do I get a group? Not really. You have to satisfy some axioms. So first, this needs to be it needs to be closed. So if we take 2 things to another thing, then you can't go out of the group. The group should involve all the elements involved in this multiplication. And then it need to be associative. So this is really what is respected by the normal multiplication. It says, let's denote this multiplication by a circle to be different, since sometimes they are. Says that I can do my multiplication in this order or the other order for any elements where I'm interested. Okay. So that's not all. Then we demand that some element called identity exists. E exists. And what we call identity is that if it multiplied by some group element, it should give it itself. Okay. And then there is, so this symbol is called there exists inverse element G inverse, such that if I multiply by G inverse and G, all G multiplied by G inverse will get our identity. Okay. You can look at the Drogler's book, Drogler's book to see that actually the left and the right inverse are the same, and the left and the right identity is also the same. They are all unique. This is a very good property because that tells us in group multiplication, we can also do this nice trick called solving equations. If this happens, we can just cancel out the A and it says B is equal to C. Okay, so this is just a property coming from the uniqueness of identity and inverse. Okay, are there any questions so far? So now we know what is a group. We shall have some examples. Okay, so let's look at the finite group. So the first example I would like you to look at is called the parity transformation. You know that P. Parity says if you give me a vector x in a space, then it just goes to minus x. Okay, you can check that if I do it again, I come back to myself, so I get a p squared equals identity. And that seems all I got. So I have a group, has two elements. One is p, one is e. The multiplication is p squared equals e. And we can check. This group has two elements, indeed satisfy our all axioms. And it is a group. Okay. So we shall move on to study a little bit more than two elements. Let's say n elements. So this is what you have learned from Tibra, is that for this equation, we can find on the complex plane, we can find n roots. It turns out all these n roots, if we put them together in a set, they also form a group. And the multiplication is just the complex number multiplication. This is known as the cyclic group. Well, since it's multiplication, that we know that, and we can also find the identity because one is a solution, and we can find the inverse. So there is also a geometry interpretation of the cyclic group, which involves us to look at some polygons. So I have to take n to be some specific number. So let's take it to be a very large number. Say 3. Okay, so let me draw the 3 complex roots. One would be here. That will be actually the, right, sorry. I should define my roots. That is e to the I 2 pi over n. Oh, notation problem. It's kind of e to a is e to the I times 2 pi over n times a. And in that sense, this will be the last root. And this guy will be the first root. And then this will be the second root. So we can also describe this cyclic group as the symmetry of this triangle. I can certainly define a transformation as, let me take a point z1 to z2, z2 to z3, z3 to z1. It's a transformation, and the triangle rotates. And then let's do it again. So then we get that z1 goes to z3, z3 goes to z2, and z2 goes to z1. And then there's always the identity, doing 3 times or doing nothing. Okay. And we can check. This transformation also describes the same group, C3. Ah, right. I have to talk about why I call them the same group or equal group. We'll get to that. Okay. But that's how much I want to talk about finite groups. Since n3 is a very large number, we can immediately go to infinity. Right? What string theories tell us. So the next step is move to infinity. So let's talk about the group with infinite number of entries, elements, but not continuous. So, I mean, a classical example is called integers. Let's define the multiplication to be addition. So as I have warned you, the multiplication in a group, but it has nothing to do with multiplication. In this case, it's addition. So let's check. We know that addition is associative. While it's close, if you add 2 integers together, you're going to get an integer. And then identity, right? So identity equals 0. If you add a 0 to an integer, you get it solved. Question. And the inverse, let's write carefully, says n inverse under the multiplication of addition is minus n. So, since it's a fine group. Multiplication is slightly funny, but it's group by our definitions. Okay, so let's look at one more example, which is integer. Now let's define our multiplication to actually be multiplication. Is this a group? No. Why not? It's multiplication, so it definitely satisfies associative.
No inverse.
The inverse isn't an integer.
Very good. There is no inverse. Oh, I should say A inverse is not in the integers. Very good. Now we all know what is group. So we should quickly move to even more elements such that we can't even count, which is called continuous. And that is our main topic of the course, which is called Lie groups. So what are Lie groups? It says, let's see G is a Lie group, and let me take an element. Then they say this element now would depend on some continuous parameters. I use phi tilde to denote a set of such parameters. Let's say there are n of them. Okay, so a group element now depends on some continuous parameters. Okay, I think the best way to understand this would be still, let's look at some examples. Okay. So let's start with rotations in 2 dimensions. Okay, by which I meant I'm an observer in 2D, imagine I'm only 2D. Then what I can do, become other observer, is rotate myself. And that is described by the rotation angle. Oh, we could draw it as we have Cartesian xy coordinate, and then it's so rotated to somewhere else called x prime coordinate. And we know this rotation is defined by this angle. So we know rotations in 2D is defined by a group element depended on one parameter, which is j of, we can choose it to be theta. So as we say, after we deal with 2, then we can immediately go to a large number 3. So in 3 dimensions. Okay, so in addition of rotating myself as before in 2D, now I have more freedom to do such rotations or such rotations. Because in 3-dimensional, we have 3 2D planes. I have xy plane, I have xz plane, and I have yz plane. And such, if we say there's an element, then it should depend on theta 1, theta 2, theta 3, 3 rotational angles. Okay. Any questions? So, as we said, now we can go to infinity. Well, go to a large number, even larger number. So, but the problem is that I don't believe in dimensions. So I can't imagine how I could rotate myself, and I'm also not an n-dimensional object. So that's a little bit troublesome. So we shall look at our 3D rotations with even more care, such that we can generalize. Okay. So let's examine the space, the 3D Euclidean space that we talk about these rotations. Well, so let's revisit. We just visited like 1 minute ago. Revisit 3D rotations. Well, let's stick with Euclidean. I like stuff I know. Okay. I also like the stuff I don't know. That's why I learned physics. But okay, let's revisit this. For 3D Euclidean space. Okay, it's a vector space, as you might realize from our tutorial 0. So it has a typical vector. And we can expand it in some basis. And we happily call this basis EI, and then we demand them to be orthonormal. Just be nice. And then, oh, right, I've already written this, is that there is a summation down here, but then it's admitted by Einstein convention. And I assure you that in tomorrow's tutorial, you will realize that admitting these summation signs are very, very helpful. There are lots of them. So our convention is whenever we say a pair of indices, then they are always summed unless somebody says no sum. So which means we also should pay attention in one equation, we should always only have a pair of indices. If you have 5 of them, then we don't really know what to do with them. Okay. So then, this space is very nice because it comes with a scalar product that I'm very familiar with. Says that if I'm given a vector x and then given another vector y, then I happily just multiply their components, add them up together. Well, I'll write another time. There is a summation somewhere, but we'll never write them anymore. Okay. Scalar product, very good. Once we have a scalar product, I can define norm, also known as the length of the vector. So I can define this vector x has some length square equals the inner product of it and itself. And then we have metric. So the metric GEIG would just be the inner product of our bases. And as I would say, we nicely chose them to be orthonormal. We just have a third ID, which is the chronicle third symbol, says that it's 1 if I equals j, and it's 0 if I is not equals j. So this is what we know about our three-dimensional Euclidean space. And what is rotation then? Well, with lect, our rotation has the following property, is that it preserves the norm. If we rotate a vector, we hope that the length of the vector doesn't change. Match my intuition. So we demand that x, so if there is a rotation, let's call it r, sending vector x to some vector x prime, then we hope that our norm that we just defined should remain the same. Okay. This, well, when we do inner product, there is a transpose going on. So if we plug this formula on the left-hand side, we get x r transpose r. We have to transpose of the column into a row to find the inner product. So then we demand this equals to our original norm. And this tells us our t, our transpose, times r equals 1. And you can show that the GIG prime under such rotations, which is defined to be the inner product of our new basis, will be equals to GIG, which says the rotation, which is still the ID. So that says that if we have a rotation, first of all, we have RT times R equals 1. And also that our metric is preserved. So those are equivalent definition of rotations. And we love this definition. Because then we say, wait, there has nothing to do with the fact that we are living in 3 dimensions. We can easily generalize to n. Okay, which is what we call a orthogonal n group. And this group is exactly defined by RT, R equals 1. Since we're very good with matrix multiplication, let's use this definition. Okay, so we take where R is n by n matrices with real entries. As we generalized from a 3D Euclidean space we live in, which have real numbers. Okay, so let's look at this matrix equation. I remember when I was doing linear algebra. Whenever I see a matrix equation, the first thing I would like, let's take the determinant, see what happens. So let's do that. Then we realize that determinant of R transpose is just determinant of R itself. We get something squared equals 1, so we get the determinant of R is plus minus 1. And I claim determinant of R equals plus 1 is special. So why do you think it's special?
Determinant of the identity is 1?
Very good. Thank you. That we have just emphasized identity is very dear to us. And it lives in determinant R equals plus 1. And this gives us the SON, which is, say, all the matrices that satisfy this condition and determinant of R is 1. So I hope after the next class, you'll be happy to claim that identity is very important for us. Okay, so we get the first set of Lie groups that we are very interested in. It comes from very nice things that we live with, which is rotations. And before we move on to other groups, there's one thing we need to do all the time. Whenever you're given the Lie groups, that should be the first thing you do. You ask how many real parameters there are. Okay, so let's do some parameter counting. Well, real parameter counting. Okay, so this thing, let's call it number n, small n. Small n. This will be called the dimension of the Lie group. Okay. And in the next lecture, we'll develop new feelings of the number of the real parameters. But we'll first count them. Okay. So I'm counting in a very naive way. That way I just said, say if I choose 2 axes to form a 2-plane, then I manage to do a rotation, as I demonstrated all these rotations. Then I say, okay, I'll just choose 2 axes from this n axis. So let me choose 1, and I can't choose the same, and the order doesn't matter. So I have, very good. I have my results. The number of parameters is just n times n minus 1 divided by 2. I like this formula. This is the first important formula of the day, so let's put it in a box. Okay. Then some people might think, well, you don't live there. How did you know your intuition is right? So let's be slightly more rigorous by counting in a different way, which is a very systematic way, in case we don't have intuition sometimes. Okay, let's count again. Well, hopefully we get the same number. Okay, count again. So ON. Well, let's do it rigorously. It's defined by the bunch of matrices to satisfy these equations. So what we're going to do is we're going to count how many entries are there. Well, it's n by n real matrices. Same as n squared is the number of entries. Then we count independent equations that you probably are familiar with, very young, that if we have the equation, then we lose a parameter. So let's count how many equations we have. Well, we have n squared equations. But the question is, how many of them are actually independent? In that case, I'd like actually restore the indices. So that will be Rij, Rik equals delta Ik, delta Jk. So that means it's transposed because we're summing those two indices instead. So if we look at these equations, we can certainly switch the indices. And so this guy becomes that guy becomes that guy, and the delta Jk and delta Kj is the same thing. So what we realize, these equations are symmetric. So our question about how many independent parameters become the question if I draw a n by n matrices, how many entries do I have if it's symmetric? Well, I can choose to be the upper angle, or the lower angle. So this angle has n times n plus 1 divided by 2 entries. We all counted entries of matrices before, right? Okay, very good. So now we know that small n must be all the entries we have, subtract the guys taken away by the equations. And this one again, it's the same guy we calculated before. The intuition actually works. Hooray. Okay, so then we shall talk about the next list of groups that we're interested in. The next set of groups, well, it's another generalization. We're talking about, matrices with real entries. And of course, if you have learned about complex numbers, you would wonder what happens if they are complex entries. So that would be our unitary n group, which the definition is just U dagger equals U equals 1. Surprise. The unitary guys come back. And now, U are n by n complex matrices. Okay, so that definitely defines a group. Okay, so the next thing we're going to do, we'll find the special guy. So let's take our determinant again. Because the special guy has identity, so we want to find it. And this, we have a slight problem because U dagger is U transpose complex conjugate. So we don't really get delta U square, we get delta U modular square equals 1. And we know that the determinant of U can be e to the I theta, which is again what the Tipper taught you. Apply to n equals 2. And then we demand the determinant to be 1. And then call them the special unitary group, SUN. And you probably have recorded from our course outline, we'll spend a lot of time with them. Okay, actually, we'll spend a lot of time with them because we're going to devote our second tutorial entirely on SU2. And it will be showing very interesting things. This SO3 and SU2, they are somewhat similar, but not quite. Somewhat equivalent to up to a factor of 2. But let me get to that. Okay, so again, we have a bunch of groups we're interested. We shall count the parameters. Well, if you have a group, you always want to ask how many dimensions it have. So, parameter counting. Well, I'm certain I'm not living in complex planes. So this time I have no intuition. So I have no choice but to do it the rigorous way. I have equations as u dagger u equals 1. And this guy has more entries because each of them is a complex number. Now we have 2n squared entries. Real. Okay. And number of equations. Well, we have n squared complex equations. But how many of them are actually independent? Okay. Let's make an observation. If we take the adjoint of u dagger u, which you must be familiar with because it's the second problem on the tutorial 0, it becomes u dagger. U dagger dagger, which is itself. And I realized, interesting. This thing we claim to be identity is actually self-adjoint or Hermitian. That throws away half of the equations. So we have n squared complex equations, so 2n squared real equation, but actually we only have n squared equations, independent equations. And it's because this guy is Hermitian. Or you can just write a 2 by 2 matrices, and you realize that the diagonal ones are real already. It's a bunch of modular square, and the off diagonals are just look like each other. Okay. So, well, the counting is using the entries, subtract the independent numbers, then we're left with n squared real parameters. So U1 has dimension n squared. Okay. Now the question is, what about special groups? Since I claimed so much that how much I love identity. So what about SO1? If On has n times n minus 1 divided by 2 parameters, how many parameters would SO1 have? Remember what we do is we throw away the determinant equals minus 1. So we basically throw away, we didn't really get rid of any real parameters. This is really saying, look, we have the x-axis. I can describe this as a one-dimensional line described by one continuous parameter. Now I cut it in half, says I only have the positive x-axis. Well, I still have to use one parameter to describe it. So for SO1, no parameter is lost. It still have this many parameters. What about for SU1? If U1 has n squared parameters, how many do you think SU1 has? When we take the determinant of U to be 1, instead of EI theta, did we lose parameter? Yes? No? There is this one parameter theta get lost. This guy used to be able to choose between 0 and 2 pi, and then when he says, no, I don't want you. So in SU1, we did lose a parameter. So the dimension of SU1 is n squared minus 1. And this is one of the most important formula we encounter today. So let's draw a box around it. It's so important that you might be asked about it in your quantum field theory 2 interview. Some inside info tell me. Okay. So let's look at the Poincare group that describe the symmetry of our world locally. So this guy has some Lorentz, is made of Lorentz group, which is described by some 4x4 matrix lambda mu nu, where mu nu goes to from 1 to 4. And then using the same idea that all these groups, that what they do is they preserve the metric. And the Minkowski space have a diagonal metric which is -1, 1, 1. Well, these are called the gravitational physics conventions. The particle physics like choose the other way around. But anyway, it's 1 negative, 3 positive. And this will be Neal's convention if it doesn't change it. Okay, so this is our convention for now. And then we claim this group shall preserve the metric. So what we demand is lambda transpose eta times lambda should go back to eta. So this is a matrix equation, which you will see in tomorrow's tutorial. You will be asked to prove Lorentz group is actually a group. Okay, which we can also write out all the indices such that we have a eta mu nu that we want to multiply by the transpose and change that guy to rho, and then multiply by nu sigma. So that guy is not next to each other, so this guy is a transpose, and these two nu's are next to each other, so it's not. So this will be the matrix with indices restored that to express a Lorentz group. So we define Lorentz group to be all these matrices that satisfy this matrix equation. So in Neal's course, we will explore a lot more with all these up and down indices that they will tell us how tensors transform, for example. But at this moment, we'll be just happy with that if I act this eta, so if I have something called x mu, I can use this metric to pull it down. So we'll be happy with how to deal with it for now, and we'll try to understand the deep stuff behind it later. And you will be play with this matrix a lot tomorrow. I meant a lot. Okay. So this is our Lorentz group. It's a bunch of matrices that preserve this metric. So A, it is, fits our description of the orthogonal group, which we should say it's O. 1, 3, we use this comma to indicate that the metric is not Euclidean. Further, we have a translation group. Which just take a x mu prime moved a little bit by a mu. And this guy is called R13. And our Poincare group, as we will examine very carefully tomorrow in the tutorial, is a semi-direct product of these two. Okay, we'll talk about this semi-direct product when I first define direct product in about 5 minutes. Okay, so this is our focus, is our tutorial's focus tomorrow. We're going to do a very, very, very complete examination of this thing. Important thing. I give you a group. So what shall we do? Let's count parameters. Well, this is a 4 by 4 matrices, and it's orthogonal. So this guy has 4 times 3 divided by 2, 6. And then this is 4 translations, so it has 4 parameters. 4, A1, A2, A3, A0. Thus, our Poincare group has 10 parameters. This is also a very important number that you might have heard of. We'll hear about it for relativity. Okay, so there are other interesting groups, but you will be referred to other books to talk about it. Then we shall move to our next topic, which is what I call the group trivia. So here is a trivia question for you. What is purple and commute? Somebody knows the answer. And the answer is in abelian, grape. It's purple and commute. Sorry, maybe my humor is a little nerdy, on the nerdy side. Okay, so this is group trivia. So of course, the first thing we're going to talk about is what do we mean by abelian group? Well, it commutes. So for any G1, G2 that we have, G1 circle G2 equals G2 circle G1. And such group are called abelian. Abelian is a very, very important guy. It's so important that abelian is actually lower letter. It's actually adjective, like not a name anymore. It's very important. Okay, but this is a nice property that some groups enjoy, such as the finite group right here. So this guy is abelian. This guy is also abelian because they are defined by the matrix, by normal multiplication, and they are abelian. But since we just mentioned a bunch of groups with matrices, so this guy is a non-abelian. Okay, so the next thing, as I said, I should tell you that if I gave you two groups and I claim they are equal, what do I mean by that? First, we're going to define what is homomorphic. So we call two groups are homomorphic to each other if there exists a map from G to G prime, such that it preserves multiplication, since that's our only operation in our group. So there's some relation between these two groups, that if I can find a map from the one element to the other element in another element, and this map even preserve multiplication, I guess what I mean is, let's see, a map. I'm running out of letters. Let's just call it F, very traditionally. Says that if I multiply FG1, FG2, which should be already in G prime group, then we should get FG1 multiplied by G2. So this is what we mean by a map that preserves multiplication. And if we can find such a map, then we call these two groups homomorphic. Okay, and then here comes the next definition, which is isomorphic. Okay, that's when they are already homomorphic, but then we find this map has inverse. So now they're actually one-to-one map. Then now we really know all these two groups are actually equal. I just actually erased the two equal groups. This cyclic group, they are the same group, either defined by complex numbers or some rotations of triangles. They are the same. We can map the transformation to some multiplication. Okay. So the next thing, we wonder about if we take a subset of the group, do I still get a group? But if we do, we call it a subgroup. So subgroup is if we take a subset of G, and if A is with the same multiplication still satisfy all our axioms, then it's a subgroup. Okay, of course, we always have two subgroups. One is called the identity. One is called J itself. These are always there. And hence, we think they are trivial. Okay. And then there's something called an invariant subgroup. So of course, at first, we got to be a subgroup. So if we already have a subgroup A, so let's take some member G and take some member A from the subgroup. Then if this thing happens, if G inverse multiplied by A multiplied by G, so you do something with this group element G back and forth. And if we find the still come back to our subgroup, then we call this subgroup invariant. And for a trivial observation, well, if they commute, then all the subgroup will be invariant subgroup. So if G is abelian group or group, then all subgroup are invariant. Okay, so do we have examples for subgroup that is not invariant? Yes, we do. So we take our three-dimensional rotations. Then if rotating around the z-axis is a subgroup of those rotations around all possible angles. But it's not invariant. If you rotate around the x, and then you rotate around the z, and then you rotate around z again, you wouldn't be in the same shape or same orientation. Okay. So now we're going to tell you something about direct product, which is one common way to make our groups bigger. Such what the standard model do. Okay. So the last thing, of all these interesting properties we want to study is the direct product. So if I have group G and the group G prime, I want to define what's G multiplied by G prime. So direct product is defined to be this way. We make an ordered pair. We take an element from G, take an element from G prime, put them into parentheses. Then we're happy. That's our direct product. Wait, but now I have a set. I need a multiplication as well. So I'm going to define the multiplication in this direct product group. So I take two of this ordered pair thing. I wonder, how do I multiply them together? It's called a direct product. Says, well, let's just multiply G1, G2 using the multiplication in G. And then multiply the G1 prime and the G2 prime using the multiplication in G prime. And then put them together again in ordered pair. Then we get the direct product of G times G prime. Now this is very good. We successfully make our group bigger, but not more complicated. And we observe such, see, like example, what I can also do is we take a G1 to be such an ordered pair as we'll take a G from the first group. But I will only take the identity from the second group. This guy is a subgroup of our direct product. Furthermore, it's an invariant subgroup. So let's come back to what we talked about. Then we say, well, actually, Poincare group is a semi-direct product of Lorentz group and R13. This is what you will prove in the tutorial tomorrow. So I take an lambda 1 and take an A1. Then I take a lambda 2, take an A2. So this is a transformation, then we multiply them together. I'm going to try to find what it comes up to be. And this does not equal to the simple multiplying two groups together. So that's why it's a semi-direct product. And if we go through the entire tutorial, we're going to realize that the R13, the translational group part, is the invariant subgroup. Well, times the identity, with the identity, is the invariant subgroup. But the other guy, the Lorentz group with the identity and the translation, is not an invariant subgroup. So it's semi, half of them. Like we make a bigger group with two parts, but one of them is an invariant subgroup, but the other one isn't. So it's called a semi-direct product. If we have a direct product, then both parts should make an invariant subgroup like this. Okay. Well, I think I'll stop here. So tomorrow we'll start talking about representations, and we'll discuss the structure of the group. Then we'll look at this guy more carefully. Then we'll spend the entire tutorial look at this guy even more carefully. Okay, so here we go.